Hi, this is Brooke Montgomery,
And Leroy Baltazar.
and this is our automated plant cover for ME106. So the idea behind this is that one day I saw an older woman moving all of her plants out of the direct sunlight and into a more shaded area of her garden. And after doing some research, we found that different plants require different amounts of light. One of the most So certain plants are light shade plants, which means that they ideally grow in 6 hours of sunlight a day, and others are partial shade, which require about 4 hours of sunlight a day. And we figured certain people are busy, they may have work or school, and they won't have time to maintain a plant that requires this much attention. So our idea is to make that whole process automated. You can just turn it on and it will do this all for you. So a list of the electrical parts first are that we have a photoresistor here at the top to measure the light that the mechanism is receiving. Then we have a temperature sensor down here in the bottom right. We have LEDs to signal some input settings that the user will decide. We also have some tack switches, a transistor at the bottom left for our power interface. We also have a continuous rotation servo, which adjusts the cover. And then we have a limit switch down at the bottom to protect everything. Our mechanical parts include a PVC pipe, a hobby fan, of course lots of duct tape, and some popsicle sticks. So how it works is you begin by inputting a zone setting by pushing the tack switch at the bottom right, and it displays zones 0 through 12 in binary. These zones have the lower temperatures allowed. So like zone 0, for example, is negative 60 degrees Fahrenheit, or zone 6 is 0 degrees Fahrenheit. The lowest temperature that a plant in that zone can survive at.
You should have, but no.
Next we have yellow LED, and when the temperature reading is lower than the zone setting, the green LED will come on as a warning. The yellow LEDs signify the amount of daylight that the plant will receive, either 4 hours or 6 hours. So right now we have the settings are zone 3 and 4 hours of daylight a day. And then the photoresistor is what gives the data to the Arduino, and it will measure the amount of daylight received by the plant, and then the servo will adjust the cover as necessary.
Okay, so right here we have our continuous rotation servo, and you can see it's well attached to one side of the hobby fan. So the photoresistor up here on top, and the temperature sensor down here below, along with the settings based on the LEDs and the user input, will use the software to correctly actuate the servo depending on the data received. So right now, the servo is set to the closed position, and when the conditions when certain conditions are met, the servo will open the fan and will provide shade for this immediate area. So, like I said, right now there are 4 main states for the servo. Right now it's closed, providing no shade. So the second state is opening. In this case, when the sunlight is shining on the plant, a timer will start. So I could try that right now. So right now we have it set it to just a few seconds of sunlight, just for demonstration purposes. I'll be using a phone light. So right now the photoresistor is reading highlight. So what just happened is that the photoresistor read that there was a certain amount of daylight, and so after a few seconds, the servo will open the shade, and the exact time of how long it will take for the shade to open is based on the user input. So like we said earlier, the partial shade plants and the full, light shade plants will require a different amount of sunlight, and that will all be based on the photoresistor's reading. After the day is done, when it is dark, the servo will close, allowing the plant to be exposed to the sun again, and it will prepare the whole cycle again for the next day. So basically, why is this helpful? Basically, all of this is automated, so during the day, you can just leave this all alone. As you can see, this can be placed outdoors, and then all the readings are conducted by the temperature sensor and the photoresistor. And then all of the actuation will occur based on the programming. The software makes sure that the plants receive the correct amount of sunlight consistently, even if one day the sun rises later or sun sets earlier. That will all be controlled. And also the LEDs are very bright and they display the appropriate information depending on what conditions are currently met. So putting together this project, we learned a lot of things about mechatronics in general. One of the main things is that all parts need to be continually assembled, tested, and retested, meaning basically from top to bottom, there's maybe different sections. Say like there's this kind of mechanism, and then there's the power interface, obviously. And then of course this shield that covers all the circuitry. All the mechanical parts, such as this moving servo, the structure itself, the electrical components, and then the software installed to the Arduino need to be in synchronization, and they need to be built in unison. One of the other things we learned is that having a modular nature is very useful. This means that it's very helpful to have components that are easily assembled, disassembled, and tested individually. For example, in the process of making this project, we were able to test just the servo by itself without having it connected to the pipe. And then we were also using the pipe as a stable structure. And we were able to test that each part on its own. Same thing with the LEDs and the power interfaces. Each part we were able to test and then individually, and then we were able to combine it. So having that was very helpful. For the coding, we actually recently learned in lecture state-based programming, which is using a case switch statement to allow us to identify various states for the servo. In our case, the servo had four main states, which is closed, opening, opened, and closing. So each of these states would switch from one to the other based on the readings of the daylight sensor and the temperature sensor. Another thing that we learned was it was very helpful that we had a diverse skill set between Brooke and myself. A lot of components required a lot of different kind of actions. For example, the soldering of the circuit board, coding of the Arduino, right around here, designing the sort of structure for it for stability and strength. And also the fact that we were able to come up with the idea of how to fit together all these mechanical components from bottom to top, and how we used various fasteners such as hot glue and tape to tie it all together. And then, of course, building the circuit required extensive knowledge of electrical engineering and basically how to control the signal, and as well as how to control the various voltage devices that we have in use here, such as our power interfaces.
And of course, there are many improvements that we could have made. Unfortunately, we had limited time and funding, but some of the things is the stability is a factor. Now it is stable, it won't fall over, but on an uneven surface, there's a little bit of wobbling. So to change this, we could have maybe had a base where we tied the bottom of the stand to. Right now it's very mobile, and that worked well for us. We also could have used more standardized parts and fasteners rather than just duct tape. Possibly even fabricated something using the laser printer. We could have made specialized parts for our exact scenario. What worked well for us is the weight. It's very light. It's very easy to move around. So if you maybe have a garden and you want to change where it is day to day, that's no big deal. We could have, again, with more fabricated parts, we could have made it even more modular in that we could have made all of these separate and easier to take apart. And it would just click together like a puzzle piece when we were ready to assemble the entire project. For electrical improvements, we could have added a LCD or LED display using either a decoder chip or an actual LCD display that are available to buy, because not everyone knows binary. And that would have displayed temperature, zone settings, daylight settings, for more cohesive information on everything. We could have also used a high torque servo. As it is right now, this servo does stall out after about 230 degrees of rotation. The reason we don't have one is that we are using in our power interface a high side drive NPN transistor setup. So the only available voltage we have is about 4.3 volts to drop across a hobby servo. We could have used a PNP transistor or possibly connected an op amp to the base of our NPN to allow for a higher available voltage drop, and thus a higher torque servo. Then we would get full rotation and more coverage. And so that's the end. This is the automatic plant cover.